Hey guys, I just wanted to make a quick video about the arterial blood gas problems. I know they can be kind of troubling sometimes, and I don't know, I had the chemistry ClinPrac test a while ago, and so I sort of relearned all this myself, taught it to myself, and I just wanted to make a quick video to sort of explain some tricks and tips about it, just because I may not have time to, I don't know, go over with it in person, um, either tomorrow or Wednesday after those other tests. So just wanted to kind of shoot over this little rough and tumble, kind of quick, cut and dry, I guess, guide that I made really quick. That just kind of takes a few points and really hammers them home. Um, and so hopefully it's not too clunky. Hopefully it'll work and can learn a little bit about it, because once you kind of get this down, these can be pretty easy points, relatively speaking. Just to jump into it though, so we know in these problems, kind of when they give us a problem, they'll give us different measurements or lab values, and usually the arterial blood gas measurements will consist of the pH, the PCO2, the partial pressure of carbon dioxide, the bicarbonate, and they'll also throw in sometimes perhaps the partial pressure of oxygen or dissolved carbon dioxide. I think for these problems, we can kind of just throw those out, at least those two values. You really only need these three: pH, partial pressure of CO2, and bicarbonate. Um, and so here you want to write these down and memorize them. They're not too tough. We have the pH of blood is 7.35 to 7.45. The PCO2 is going to be 35 to 45 millimeters of mercury. Easy way to remember that is just kind of this 35 and this 45. Well, that's your PCO2, 35 and 45. And then the bicarbonate is going to be 22 to 26 millimoles per liter. There are a couple of different reference ranges for those on our AMA packet that we got a long time ago in Bridge to Clinical Prac. It was like 21 to 28, but this 22 to 26 millimoles per liter, that's kind of what we see in our chem book. So I would go with that. I think that's the one that they usually use. And I kind of put this right here, this milliequivalents per liter. They might give it to us in those units, but essentially they're exactly equivalent. So it can be 22 to 26 millimoles or 22 to 26 milliequivalents. So just copy those down, memorize them, kind of set them in your brain. They'll become important in a little while. Moving on, we've got this pH scale. It's pretty simple. As we said before, the pH of blood is 7.35 to 7.45. And then we know that if the pH is below that 7.35, it's acidosis. And if the pH is above 7.45, it's alkalosis. And so that's kind of a good visual aid to look back at. Next, this is kind of pretty important, I think, just to kind of have a concept of what's going on in the body. And we can kind of treat these as the lungs and the kidneys. The lungs are going to control CO2, which you should think about as your acid component. And so when you exhale more, um, you're going to get rid of that acid component, and the pH is going to go up, so it'll become more alkalytic. But if you exhale less, you're going to be retaining that CO2, and so the pH is going to decrease. It's going to become more acidic. So that's important. The kidneys, on the other hand, they control the bicarbonate, which you should consider as your base product. And so the kidneys, when they secrete more bicarbonate, they're getting rid of the base and decreasing the pH. If they retain more bicarbonate, they're going to hold on to it and increase the pH. So it's going to become more basic. And then next, these are kind of where you want to drive it home these two rules, as I like to think of them. And those are respiratory disorders. They equal when the CO2 goes opposite of pH. And if that's kind of confusing, that's okay. We'll kind of see how that will apply in just a few seconds. But just remember these two rules. So respiratory disorders, CO2 goes opposite of pH. For metabolic disorders, the bicarbonate goes the same as pH. You can sort of remember that with this acronym of ROAM. So respiratory is opposite, metabolic is equal or the same. So really, if you come away with nothing else, try and remember these, I guess, general guidelines or rules, as I like to think of them. And the kind of, so that's that. And then the kind of reason that I think it's a good deal to get behind or kind of think of in your head is just what's sort of going on in, I guess, the physiology. And so here we have kind of a simple diagram where in your tissues, your cells, they're undergoing aerobic respiration, and producing this CO2. And so the CO2 is going to dissolve out of the cell into the lumen of a blood vessel, where it will combine with water and be acted upon by this enzyme, carbonic anhydrase, to produce carbonic acid, which then will dissociate into bicarbonate and hydrogen ions. So in the blood, the bicarbonate will get carried on its way to the lungs. So you can pretend that this is sort of happening in the periphery of your body, just I guess as a aid to help you think about it. So say like this cell is in your foot or your hand that's respirating CO2 to produce the bicarbonate, and then blood flow will take it to the lungs. So then it will come down here, and from the tissues from your foot or your hand, that bicarbonate's coming along, and then carbonic anhydrase will act upon it again to produce this carbonic acid, which will then be converted into, again, carbon dioxide and water. The carbon dioxide will dissolve out of the blood vessel into the alveoli of the lungs through that, and then be blown off, from the lungs. So we've got this process, and you can kind of relate it back, at least for the lungs, to the system we sort of discussed here. They control the CO2, which is your acid component. So when you exhale more, again, you're blowing off the CO2, getting rid of the acid, and increasing the pH. If you exhale less, you're retaining CO2, retaining more acid, and decreasing the pH. And the kidneys are pretty simple. They're just kind of either getting rid of the bicarbonate or retaining more. And so I didn't really represent those here. But that's sort of what you kind of need to understand in a way to explain, the why of it. When they ask us those questions, why is something in metabolic acidosis or respiratory alkalosis? You can sort of think back to this diagram, and it should help you out just a little bit. And so that's that equation. Technically, this equation does happen in the red blood cell. That's where the carbonic anhydrase is located. But that's just, for, bonus learning, I guess. So the CO2 is coming out of the cells in the plasma. It's dissolving into the red blood cell. It's going through that reaction to produce bicarbonate and hydrogen. The hydrogen will actually be buffered by hemoglobin. The bicarbonate will dissolve out of the cell, and then to retain the electrical neutrality, a chloride ion will dissolve into the red blood cell. And that's, I don't know if y'all remember the chloride shift, but you can sort of read about it right here. And then, of course, when the red blood cell gets to the lungs, the exact opposite happens to produce your CO2, and it's blown out, which you can pause